The oldest light in existence has a bruise on it, a cold, empty wound carved into the sky, 1 billion light-years wide, and scientists still cannot explain it. Right now, galaxy clusters containing billions of stars are all drifting in the same direction, pulled by something massive hiding beyond the edge of everything we can see. The equations governing our cosmos are quietly breaking. Tonight, we travel to the edge of the observable universe, into laboratories where physicists search for what presses against us from outside, and into the mathematics that keep demanding an answer our universe alone cannot provide. If you enjoy this journey, subscribe and leave a like. Take a breath. We launch into the deep. Picture the universe as a sphere. Every direction you look from Earth, you can see roughly 46 billion light-years before the light simply runs out. That boundary is called the observable universe, and for most of scientific history, we assumed nothing beyond it mattered. We assumed it was just more of the same, endless space, endless galaxies, following the same rules we know here. That assumption is beginning to crack. The observable boundary is real, but it is a limit of our vision, the edge of how far light has had time to travel since the Big Bang. The actual universe, the full structure, stretches far beyond what we can ever see. Theoretical models suggest it could be hundreds, thousands, or even infinitely larger than our observable pocket. And in something that large, in something that stretches without end, strange things are allowed to happen. For decades, cosmologists treated the region beyond the horizon as irrelevant, unreachable, unknowable. Whatever sat out there could not affect us, because nothing travels faster than light, and the space between here and there was simply too vast. That logic seemed airtight. But gravity does not care about distance the way light does. Gravity is not a signal traveling through space. Gravity is a property of space-time geometry itself, and geometry does not stop at the edge of our vision. Recent observations are showing patterns in our universe, alignments, flows, anomalies that are too large and too consistent to have come from inside our observable bubble alone. Something is organizing matter on a scale bigger than anything we should be able to see. The universe we thought we lived in, isolated, self-contained, sealed from outside influence, may be nothing more than a small room inside a structure of staggering complexity. And whatever fills that larger structure may already be reaching through the walls. Here is why that matters for you. Every atom in your body, every force holding this planet together, every constant of nature that makes chemistry possible, these values were set in the first moments of our universe. If something external influenced those first moments, then something external helped shape the conditions that made you possible. The question of what exists beyond our universe is not an abstract philosophical puzzle. It is a question about the origin of physical reality itself. But before we get to what might be pressing in from outside, we need to understand why our universe itself is already misbehaving on the inside. Because the numbers are not adding up, and physicists are starting to run out of comfortable explanations. Consider what it means to say the equations are breaking. These are equations that have been tested against every observation for decades. They predicted the abundance of hydrogen and helium in the cosmos with extraordinary precision. They predicted the pattern of galaxies across billions of light years. They predicted the temperature of the oldest light in the universe to 7 decimal places. These are not weak equations. They are the most tested and most successful framework in the history of science. And they are giving the wrong answer. Something that should agree with itself across every measurement is instead producing a contradiction. Whatever is causing that contradiction is real, and it is in our universe right now. What comes next changed everything scientists thought they knew about expansion, and the gap it opened has only grown wider with every new measurement. Our universe is expanding. That has been confirmed for nearly a century. Every galaxy beyond our local group is moving away from us, carried outward by the stretching of space itself. The question that seemed settled was simply, how fast? It turns out the answer depends on how you measure it, and the two best methods disagree. The first method examines the early universe directly. Satellites have mapped the cosmic microwave background, the faint glow of radiation left over from the Big Bang, with extraordinary precision. By measuring the patterns in that ancient light and running the equations of cosmology forward in time, physicists can calculate how fast the universe should be expanding today. The result is a precise number. The second method looks at the present-day universe. Astronomers measure the brightness of specific types of exploding stars called Type 1a supernovae, which always explode with a known luminosity. By comparing how bright they appear from Earth to how bright they should be, astronomers can calculate how fast the universe is expanding right now. The result is also a precise number. The two numbers do not match. The universe measured today is expanding faster than the universe measured in the ancient light predicts it should be. Both methods have been checked and rechecked by independent teams using different instruments and different techniques. The disagreement has not gone away. It has grown more stubborn and more precise with every new data set. This is called the Hubble tension, and it is one of the most alarming unsolved problems in modern cosmology. The gap seems technical until you understand what it implies. If both measurements are correct, then something is adding energy to the expansion of the universe that our standard model of cosmology does not include. Something is pushing space apart faster than the physics inside our universe alone can account for. Standard explanations have been proposed and examined carefully. Unknown behavior in dark energy, new species of particles affecting the early universe, subtle errors in the cosmic distance ladder. None of them fully close the gap. None have been confirmed. One category of explanation that keeps surfacing in theoretical papers involves influence from outside the observable universe. If something beyond our horizon is exerting gravitational or energetic pressure on our region of space, that pressure could manifest as an anomalous acceleration in the expansion rate, an invisible hand pushing from a direction we cannot see. The tension has not resolved. If anything, it has deepened, and that matters because the Hubble constant governs everything we think we know about the age and size of our cosmos. A universe expanding faster than our oldest measurements predict is a younger universe, a different universe, a universe with different properties than our best theories describe. Every structure in the cosmos, every galaxy cluster, every great wall of matter stretching across hundreds of millions of light years sits at a slightly different place in the timeline depending on which measurement you trust. The disagreement is not a small technical footnote. It is a fault line running through the foundation of modern cosmology, and the longer it persists, the more seriously physicists are forced to consider that something is missing from every model they have. The next anomaly makes the tension look almost routine, because this one you can point to in the sky and see. In 2004, Astronomers analyzing the cosmic microwave background found something that should not exist: a region of space approximately 1 billion light-years across, where the temperature of that ancient radiation is significantly colder than everything surrounding it. Colder in a specific structured way. Colder in a way that the best cosmological models cannot fully explain. This is known as the cold spot, and nearly 20 years of analysis have not resolved it. The cosmic microwave background is remarkably uniform. It fills the entire sky in every direction and varies in temperature by only tiny fractions of a degree. Those tiny variations carry enormous information about the early universe, how matter clumped, how structures eventually formed, where galaxies would grow. Cosmologists have mapped it in extraordinary detail and understand most of it very well. The cold spot does not fit the pattern. It is too large, too cold, and too structured. Statistical analyses suggest the probability of it appearing randomly within the standard cosmological model sits around 1 in 50. That does not sound alarming until you consider that cosmologists have been arguing about it for 2 decades without a resolution, which means no routine explanation has managed to stick. One mainstream candidate is a supervoid, an enormous region of space relatively empty of galaxies. Light passing through an underdense region loses energy in a specific way and arrives at our detectors slightly colder. Surveys of galaxies in that direction have found a possible supervoid, but measurements disagree on whether it is large enough or empty enough to account for the full observed cooling. The numbers fall short. The other candidate, the one that appears in careful academic papers with increasing seriousness, is that the cold spot is a bruise, a contact scar left behind by a collision between our universe and a neighboring bubble universe in the very early moments of cosmic history. In this framework, the temperature anomaly is the imprint of where 2 universes touched billions of years ago, and the boundary between them pressed against our ancient light and left a permanent mark. The collision explanation makes specific predictions about the shape and temperature profile of the anomaly. The cold spot partially matches those predictions. The match is not perfect, which either means the collision models need refinement or the cold spot has a different explanation entirely. What is confirmed is this: the cold spot is real. The anomaly is in the data. Conventional explanations have not closed the case, and in science, a 2-decade-old anomaly that refuses to yield to standard explanations is not a small thing. It is a signal. The question is what it is pointing at. There is something important about the way this anomaly has been handled by the scientific community. It appeared in the first precision maps of the microwave background. It appeared again in the second generation of satellite data. It survived every improvement in the quality of the measurement. Anomalies caused by measurement error tend to shrink as instruments improve. The cold spot has not shrunk. It has remained precisely where it is, precisely as cold as it appeared in the earliest maps, waiting for an explanation that the standard model of cosmology has not supplied. What comes next involves something far larger than a cold patch in the sky. It involves entire clusters of galaxies moving in a direction they have no business moving. In 2008, cosmologist Alexander Keshlinsky and a team of colleagues published a finding that sent a quiet tremor through the physics community. They had been studying the motion of galaxy clusters, enormous collections of thousands of galaxies bound together by gravity, and specifically their motion at the largest scales, beyond what local gravitational influences could explain. What they found violated one of the foundational assumptions of modern cosmology. Hundreds of galaxy clusters, spread across billions of light years in every direction they sampled, were all moving together. Not randomly, not following the local gravitational landscape, moving coherently in the same direction, as if something unimaginably massive far beyond everything we can see was pulling them toward it. They called it dark flow. To understand why this is so alarming, think of a river. On the surface, you see eddies and ripples moving in all directions, but the entire river flows one way. Dark flow is the cosmological equivalent of that river. At the very largest scales we can measure, matter appears to be flowing in a direction that points outside the boundary of everything we can observe. Standard cosmology strictly forbids this. After the Big Bang, the universe should have expanded in all directions with essentially equal force. The large-scale structure of the cosmos today should show no preferred direction of drift. The cosmos should look the same from any vantage point and in any direction at the biggest scales. This principle, called isotropy, is baked into every cosmological model we use. Dark flow, if real, shatters isotropy. It would mean that something beyond our observable horizon has enough gravitational influence to tug coherently on matter spread across billions of light-years of space. The source of that pull would have to be more massive than anything that could exist inside our horizon, which means it cannot be inside our horizon. Subsequent research produced complicated and sometimes contradictory results. Some teams confirmed the signal using different data sets. Others found it weakened or vanished when they applied different analysis techniques. The scientific debate continues actively in the literature today, and consensus has not been reached. But the theoretical implication does not depend on whether this specific measurement is ultimately confirmed. If dark flow is real even at a weaker level than originally claimed, it means something enormous is exerting gravitational influence from beyond the edge of our vision. The universe is being pulled somewhere, toward something, and that something is hiding behind the horizon. What makes dark flow particularly important as a concept is not whether this specific measurement survives further scrutiny. It is what the measurement implies about the relationship between our universe and whatever lies beyond its edge. The observable universe is enormous by any human standard, stretching 46 billion light-years in every direction. To exert a coherent gravitational pull across that entire span, the source would have to be almost incomprehensibly massive. It would have to represent a concentration of matter and energy greater than anything that could exist within our observable sphere. The only way to accommodate such a source is to place it outside our horizon entirely, in the region of the cosmos we can never directly observe. Something is there, something enormous, something whose gravitational reach extends across the full width of everything we can see, and we are drifting toward it at speeds that will carry the entire observable universe in that direction over the coming billions of years. In our own cosmic neighborhood, we have been watching exactly this kind of unexplained pull for decades, aimed at something we can barely see even when we look directly at it. For decades, astronomers kept noticing the same thing. Our galaxy was moving in an unexpected direction. So was our entire local group of galaxies. So were thousands of galaxies surrounding us, stretching outward in every direction we looked, all of them drifting together, pulled by the same invisible source toward the same point in the constellation Centaurus. Something enormous was pulling everything in our cosmic neighborhood toward it. The source, hidden behind the dense curtain of stars and dust in the central plane of our own galaxy, became known as the Great Attractor. It sits approximately 250 million light-years away, and for years it was nearly impossible to study because our galaxy sat directly in the line of sight, blocking the view with billions of stars and vast clouds of obscuring gas. When astronomers finally developed techniques to see through that obstruction, studying radio waves and infrared light that can pierce the dust, they found a massive concentration of galaxy clusters in that direction. A dense knot of structure called the Norma cluster sits there, with a far larger superstructure called the Shapley supercluster lurking further behind it. Together, they represent an enormous concentration of mass. Here is the problem that has persisted through decades of study. Even after accounting for all the visible mass in that direction, even after summing up every galaxy cluster, every visible concentration of matter that astronomers can measure, the gravitational pull toward the Great Attractor region is stronger than it should be. The math does not close. There is additional pull, additional gravitational influence that the visible matter cannot explain. Some physicists suspect this is the local peak of a much larger gradient that extends far beyond what we can map, perhaps all the way to the edge of our observable universe, perhaps past it. The Great Attractor in this view is simply the nearest point on a slope that descends into territory we cannot chart. We are sliding down a hill toward a valley we cannot see the bottom of. Our galaxy is moving toward the Great Attractor region at roughly 600 kilometers per second. The entire Milky Way, the solar system inside it, every continent on this planet, every person reading these words, all carried together toward something we cannot fully see and cannot fully explain. The excess pull has been known for years. Standard explanations account for most, but not all of it. Something beyond the visible mass is adding to the gravitational budget of this region of the cosmos, and that something has never been identified. The measurement of that excess has been refined repeatedly. With each improvement in the surveys and instruments used to map this region of space, the visible mass total becomes more accurate. And each time it is updated, the gap between the mass we can see and the pull we can measure does not close. It narrows in some analyses and widens in others, but it does not disappear. The gravitational accounting of our local cosmic neighborhood consistently comes up short when limited to visible sources. Some researchers argue the shortfall is within the uncertainties of the measurement. Others argue it is systematic and persistent. What both sides agree on is this: if the excess is real, there is no conventional candidate for its source within the observable region. The explanation, if it exists, lies somewhere beyond the curtain of our horizon. Think that is the strangest unsolved mystery in our local neighborhood. What comes next challenges the geometry of space itself, and it begins with a question that sounds philosophical, but turns out to have a precise scientific answer. Before going further into the evidence, we need to stop and handle a question that derails most conversations about this topic before they get started. What does it mean to say something exists outside the universe? If the universe is everything that exists, then by definition, nothing can be outside it. The phrase seems to be self-contradicting. This is a philosophical trap, and physics has a precise way out of it. When cosmologists talk about something beyond the universe, they are using the word universe in a specific technical sense. They mean the observable universe, the region of space causally connected to us, or they mean the bubble of space-time produced by our particular moment of cosmic inflation. They are not making a claim about the totality of all existence. They are asking whether the specific, bounded region of space-time we inhabit is embedded in something larger. And the answer, from the mathematics of our best confirmed theory of the early universe is almost certainly yes. Inflation theory, the leading framework for explaining the structure of the early cosmos, describes a period of extraordinarily rapid expansion in the universe's first moments. In most versions of the mathematics, this inflation never completely stops everywhere at once. It keeps happening in regions that have not yet ceased expanding, while in other regions it ends and produces a bubble of normal space, what we would call a universe. Our universe is one such bubble. Many others may exist, each expanding independently, each causally isolated from the others because the space between them is stretching faster than light can ever cross it. These other bubbles are not inside our universe. They are not outside it in the everyday sense either. They are adjacent regions of a larger space-time, separated from us by distances that can never be bridged by light or matter traveling through normal space. They are, in every practical and measurable sense, other universes. But gravity does not travel through normal space the way light does. Gravity is a property of space-time geometry, and in theoretical frameworks involving extra dimensions which appear naturally in the most mathematically consistent theories of fundamental physics, gravitational effects can propagate through dimensions that our matter cannot access. This is the mechanism by which something on the other side of the boundary could reach into our bubble and exert a measurable influence. Reaching through extra dimensions does not require faster-than-light travel. It does not violate any known law of physics. It simply requires that the cosmos has more structure than the thin three-dimensional slice we can directly observe. And the anomalies accumulating in our data are increasingly consistent with exactly that. The next anomaly is stitched across the entire sky, and the name physicists gave it tells you everything about how alarming they found it. The cosmos appears to be larger and stranger than the universe we can see, and what lies in that larger structure may already have left its fingerprints on our sky. The tools we have built to search for those fingerprints have become extraordinarily precise, and they have been finding things that our standard models did not predict. The anomalies are not going away. They are multiplying. And the next one was given a name that tells you everything about how unsettling physicists found it when they first measured it. The idea of a multiverse did not begin as speculation or science fiction. It emerged as an uncomfortable mathematical consequence of taking our best confirmed theory of the early universe entirely seriously. Inflation theory was developed in the early 1980s to solve several deep problems with the standard picture of the Big Bang. It proposed that in the universe's first tiny fraction of a second, space underwent a period of exponential expansion so rapid that regions causally connected before inflation became causally disconnected afterward, explaining why the observable universe looks so uniform in every direction, despite being far too large for light to have ever crossed it and equilibrated. The theory worked extraordinarily well. It explained the flatness of the universe, the uniformity of the microwave background, the absence of exotic relics from high-energy early physics, and the specific pattern of density fluctuations that seeded all large-scale structure. It became the leading framework in cosmology, and it predicted something enormous that nobody had asked for. In most mathematical implementations of inflation, the process that causes expansion does not stop everywhere at the same moment. In regions where the inflating field happens to drop to a low value, inflation ends and a bubble of normal space forms. Our universe is one such bubble. But in surrounding regions, The field remains high, and inflation continues indefinitely, producing more bubbles, each separated from the others by still inflating space that can never be crossed. This is called eternal inflation, and it is the standard prediction of the most successful cosmological frameworks physicists have. It means our universe is one bubble among what may be an effectively infinite number of others, each produced at different times, each potentially with different physical constants and different laws of nature, each permanently causally disconnected from all the others. For decades, the multiverse remained a theoretical consequence with no observational handle. If the other bubbles are causally disconnected from ours, how could we ever know they exist? The answer came from collision physics. Bubbles of inflation expand. In an eternally inflating space filled with expanding bubbles, collisions are statistically inevitable. Two bubbles making contact would send a shock wave through each interior, and that shock wave would leave a circular imprint on the cosmic microwave background of the bubble it passed through. We already found a circular anomaly in our ancient light. We have been staring at it for 2 decades without explanation, and now there is a theoretical framework that predicts exactly that kind of feature in exactly that location in the sky, from exactly the kind of event that physics says should have happened. That coincidence is either the most extraordinary statistical accident in the history of science, or it is evidence of something real. The scientific community's relationship with multiverse collision predictions is an instructive case study in how physics moves from speculation to empirical science. In 2007, when theoretical teams first worked out the precise signatures that a bubble collision would leave in the microwave background, the work was received with serious skepticism. The signatures were too exotic. The theory was too speculative. The prediction too convenient. By 2010, independent groups were running actual searches for those signatures in real satellite data. By 2015, the methodology had been validated, the search algorithms refined, and the next generation data collected by a more sensitive satellite was being prepared for analysis. The field moved from theoretical prediction to observational search program in under a decade. That trajectory is how physics is supposed to work. A theory makes a specific prediction. Observers build or use instruments capable of detecting the predicted signal. The search runs. When 2 soap bubbles touch in the air, they merge gently, sharing a thin wall of film between them. The physics of 2 colliding universe bubbles is incomparably more violent, and the traces it leaves are permanent. When 2 bubble universes make contact, the boundary between them is called a domain wall. This is a surface of space-time where the physical vacuum of one universe meets the physical vacuum of another. If the 2 bubbles formed at different times or with different field values, as most multiverse models predict they would, the physics on each side of that wall is different. The wall itself carries a tremendous amount of energy, concentrated into an infinitely thin boundary between 2 incompatible regions of reality. The collision sends a shock wave outward through the interior of each bubble, traveling at the speed of light from the point of contact. In our universe, that shock wave would have propagated across the sky in all directions from one specific point, spreading outward like a ring of disturbed water on a pond. As it passed through the hot plasma of our early cosmos, it would have compressed and heated matter on one side and rarefied and cooled matter on the other. That disturbance would have frozen into the cosmic microwave background as a circular or elliptical region of anomalous temperature, with a sharp edge corresponding to where the shock wave front reached. The shape would be distinctly circular because our bubble was struck from one direction, leaving a single scar rather than uniform bruising across the whole sky. Theoretical physicists have calculated precisely what this scar should look like. They have derived the expected temperature profile, the sharpness of the edge, the relationship between the size of the anomaly and the strength of the collision. The predictions are specific enough to test against real data. Teams of astronomers have run those tests. A group at University College London performed a systematic search of the microwave background data and found several candidate features, including one that aligns in position and rough temperature profile with predictions from moderate-strength universe collisions. Their analysis was careful, and their conclusions were hedged, as good science requires. Later analysis using more precise satellite data found that some of the original candidate features were weaker than hoped. The search continues, and the methodology now exists to detect such a collision if it happened and left a strong enough mark. This is a case where physics has moved from philosophy to measurement. A specific event has a specific predicted signature. The tools to look for it exist, and one anomaly in our data has refused every conventional explanation for 2 decades while matching the predicted shape of a universe collision. Gravity, though, has its own path across any boundary, and the next chapter explains how it might already be reaching us from the other side. The domain wall between 2 colliding universes is the most extreme physical boundary imaginable. On one side, the laws of physics are ours. On the other, they belong to whatever universe our bubble collided with. If that universe formed with a different vacuum energy, different particle masses, different coupling constants, the wall separating the 2 regions would be under enormous tension, like a membrane stretched between incompatible physics on each face. After the collision shock wave has passed and the universe has expanded and cooled, the domain wall remains. It sits at the edge of what the collision shock wave covered, a permanent scar in the geometry of space-time. Of all the fundamental forces, gravity is by far the strangest. It is incomparably weaker than the other 3 forces governing nature. The electromagnetic force that holds an atom together is roughly 1 followed by 36 zeros times stronger than gravity at the same distance. That gap is so enormous, it has no good analogy in everyday experience. This weakness has troubled physicists for decades. There is no good reason inside standard physics for gravity to be so much weaker than everything else. The laws of nature are remarkably precise and interconnected in ways that suggest deep structure, yet the strength of gravity seems to be set at an arbitrary and puzzling value relative to the other forces. This puzzle is called the hierarchy problem. One of the most elegant proposed solutions involves extra dimensions of space that we cannot directly access. In theories developed in the late 1990s, the other forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, are confined to our 3-dimensional slice of space. They live on what physicists call a brane, a membrane of space-time, and they cannot propagate beyond it. But gravity is different in a fundamental way. Gravity is a property of space-time geometry itself, and it propagates through all dimensions of space-time, including any extra ones that may surround our brane, like an invisible ocean, surrounding a very thin island. In this framework, gravity appears weak to us because most of its strength is leaking away into the extra dimensions we cannot access. The gravity we experience is only the fraction that happens to propagate through our thin slice of space. The rest bleeds outward in directions we have no sensory access to. Gravity is not actually weak. We are simply seeing only a small fraction of it. This has a testable consequence. At very short distances, shorter than the scale over which the extra dimensions are curled up, gravity should deviate from the expected law and appear stronger, because at those distances, the extra dimensions have not yet diluted its strength. Extremely precise experiments have tested gravity at scales smaller than the width of a human hair, looking for exactly this deviation. So far, no deviation has been found. The extra dimensions, if they exist, must be curled up smaller than the distances measured, or their geometry must suppress the effect below detectable levels. But here is the implication that matters for this story. If gravity leaks out of our universe into extra dimensions, then gravity from another brane, another region of space-time adjacent to ours, in the extra dimensions, can leak in. A massive concentration of matter on a neighboring brane, a parallel universe separated from us by a gap in dimensions we cannot see, would exert gravitational pull on our brine. We could never see that matter, we could never visit it, but we would feel its gravity, arriving from a direction that points nowhere visible. And the next thing imprinted on the oldest light in the cosmos suggests something has been doing exactly that. The hierarchy problem has been called the most embarrassing open question in physics, because gravity's weakness affects everything from the size of stars to the conditions required for life. Extra dimensions resolve the embarrassment elegantly. And if they exist, their consequences reach far beyond laboratory measurements into the full structure of the cosmos surrounding us. The cosmic microwave background is the most studied object in all of cosmology. It is a picture of the universe at 380,000 years old, the moment when matter and light first separated and radiation streamed freely across space for the first time. Imprinted on it is everything that happened in those first moments. The density fluctuations, the sound waves in the primordial plasma, the fingerprints of quantum processes that seeded all large-scale structure, and it is covered in things that should not be there. Beyond the cold spot, the full sky maps produced by satellite observatories have revealed a collection of features that do not fit the standard cosmological model. These are subtle, not dramatic, but they are statistically persistent, and they refuse to disappear as the data improves in precision. There is an unexpected asymmetry in the temperature fluctuations between the two halves of the sky. The northern galactic hemisphere and the southern galactic hemisphere look measurably different in ways they should not. Standard cosmology predicts the same physics in every direction at large scales. The asymmetry persists. There is a suppression of power on the largest scales, meaning the temperature variations at the very biggest angular separations across the sky are weaker than models predict. Inflation produces a nearly scale-invariant spectrum of fluctuations, and at the very largest scales we can measure, the observed power falls below what the theory says it should be. And several of the largest features in the microwave background appear to align with each other and with the geometry of our solar system. The orientation of the largest temperature patterns in the oldest light in the universe correlates with the plane of our planetary system. This alignment is so improbable and so conceptually troubling that it earned its own nickname inside the physics community. These anomalies could be statistical flukes. Any complex dataset will produce unusual features, and if you look hard enough at any map, you will find patterns that seem significant. But these features were predicted to possibly exist by certain theories before the data improved, and they have persisted across multiple independent satellite missions using different instruments. They could also be foreground contamination, nearby emissions from gas and dust in our galaxy that have not been perfectly subtracted from the ancient signal, but foreground removal has improved substantially with every mission, and the anomalies remain. Or they could be signatures of physics that occurred before or outside our universe, stamped into the background light at a moment when our cosmos was still young enough to carry external imprints. That possibility has moved from the margins of cosmological discussion into mainstream theoretical research. The alignment in particular has a name that tells you everything about how unsettling physicists found it when they first measured it. The full pattern of anomalies in the ancient light does not look like random noise. Random anomalies scatter across the measurement space in all directions. These anomalies cluster. They share a common character, directionality, unexpected alignments, systematic deviations that all point in the same conceptual direction. In science, clustered anomalies pointing the same way are how discoveries begin. The alignment in particular has a name that tells you everything about how unsettling physicists found it when they first measured it. This is what the next discovery revealed: a single forbidden alignment running through the entire fabric of the oldest light in the universe. The name was given in 2005 by cosmologist Kate Land and mathematician João Magejo, and it was chosen deliberately to signal just how alarming the discovery was. In a universe governed by the standard cosmological model, the large-scale features of the ancient radiation background should be completely random in their orientation across the sky. The cosmos should have no preferred direction. The processes that generated those features, quantum fluctuations amplified by inflation in the first moments of time, had no special direction built into them. The features should point every which way, averaging to no alignment at all. They do not. Several of the largest temperature patterns in the cosmic microwave background point in the same direction. That direction correlates with the geometry of our own solar system, specifically with the plane of the ecliptic, the imaginary flat surface our planet traces as it orbits our star. The largest temperature variations across the entire sky, described mathematically by terms called the quadrupole and octopole moments, are oriented along a single axis. That axis points toward the Virgo constellation and aligns with the ecliptic. The probability of this occurring by chance in a universe with no preferred direction has been calculated multiple times by independent teams. The results consistently fall somewhere between 1 in a few hundred and 1 in several thousand. 1 in a few hundred sounds manageable, but here is what matters. Cosmologists have been aware of this for 2 decades, have thrown every possible explanation at it, and have not made it go away. The alignment has survived more precise measurement. It has survived improved foreground removal. It has survived the transition from one satellite mission to the next with better instruments. Several explanations exist within standard physics. The alignment could be a statistical accident, one of the inevitable flukes that appear in any large data set. It could be residual foreground contamination from our galaxy that is subtle enough to have evaded detection. It could reflect an unusual topology for our universe, a shape that wraps back on itself in some direction and produces real correlations in the sky. The fourth possibility, the one that requires the least ad hoc modification to the underlying physics, is that something external imposed a preferred direction on our universe at or before the moment our universe's oldest light was created, that the axis of evil is the echo of a boundary condition set from outside, a direction from which something outside our universe exerted influence early enough to leave an orientation baked into the fabric of our cosmic microwave background. It points somewhere specific. Something is in that direction. There is a deeper layer to the axis alignment that makes it even more difficult to dismiss. The alignment is not between two randomly selected features of the sky. It aligns with the ecliptic, the plane in which our planet orbits our star, and with the galactic equator, the plane of our own galaxy's disk. These are the two most local and parochial coordinate systems in all of astronomy. The fact that the largest features in the oldest, light in the universe align with the geometry of our tiny planetary system, a structure that did not exist until 10 billion years after the microwave background was created, has no explanation within standard cosmology. If it is foreground contamination, then our galaxy is emitting radiation that looks exactly like a cosmological temperature pattern aligned with the ecliptic, which would require a coincidence of a different but equally alarming kind. To understand how a universe could have neighbors it cannot see, and how those neighbors could exert physical influence across the boundary between them, you need to understand what physicists mean by the word brain. In string theory and its extensions, space is not three-dimensional. It has additional dimensions curled up so tightly that they are invisible at the scales we can probe, present everywhere but inaccessible to our matter and our instruments. In the most developed versions of the theory, there are 10 dimensions of space and 1 of time. The extra 7 dimensions are present in every point of space around you, folded into a shape too small to detect. Particles of matter, and most of the forces governing them, are confined to a 3-dimensional subspace within this higher dimensional geometry. They can only move through 3 of the available dimensions. The 3-dimensional world we experience is called a brane, short for membrane, because it behaves like a surface embedded in a higher dimensional environment. Picture a sheet of paper floating in a room. Insects living on the surface of that paper exist in 2 dimensions. They can move anywhere on the sheet, they can build complex structures, they can interact with each other and with everything on the sheet's surface, but they have no access to the 3rd dimension of the room. They cannot move up or down. They cannot detect the depth of the space around them. The room could be full of other floating sheets carrying their own civilizations, and the surface insects would never know. Our universe is that sheet of paper, extended into 3 dimensions, floating in a higher dimensional space physicists call the bulk. Other branes may exist in the bulk, parallel to ours, separated by a gap in the extra dimension. They could be extraordinarily close, in the extra-dimensional sense, while being completely unreachable through any path available to matter or light. The matter on those branes emits no light that can reach us. The galaxies there cast no shadows we can see, except through gravity. Gravity propagates through all dimensions of the bulk. A massive concentration of matter on a neighboring brane would exert gravitational attraction on our brane. The pull would arrive from a direction that does not correspond to any visible source. The math would not close when astronomers tried to account for all the mass in that direction. There would be a persistent excess of gravitational pull toward a region that, when examined with every available instrument, seems emptier than the pull requires: the Great Attractor, dark flow, the unexplained excess in the gravitational budget of our local cosmic neighborhood. These anomalies fit the predicted signature of a neighboring brane pressing gravitationally on our own. Something massive may be floating just out of reach in the extra dimension, and we are feeling its weight without being able to see its face. The brain framework also offers a natural explanation for why the influence we seem to feel arrives from specific directions rather than uniformly from all sides. If a neighboring brain has finite extent and its own structure with concentrations of mass distributed unevenly across its surface, the gravitational pull on our brain would be stronger in the directions where that mass concentrates and weaker in the directions where the neighboring brain is sparse. The directional anomalies in our own sky, the Great Attractor, dark flow, the axis of evil, would all be directional for exactly this reason. We are feeling the gravitational shadow of a mass distribution on the other side of a dimensional boundary, and that distribution is lumpy, just as ours is. In September 2015, a detector in Louisiana picked up a ripple in spacetime so subtle that it moved its mirrors by less than 1/10,000th the diameter of a proton. The signal had traveled more than 1 billion light years from two merging black holes and arrived at Earth as the faintest possible whisper in the fabric of space itself. Its detection was one of the most precise measurements in the history of science, confirming a prediction made by Einstein a century earlier. Gravitational waves have since become a new sense for astronomy. Where before, we could only see the universe through electromagnetic radiation of various wavelengths, we can now hear it through ripples in space-time, detecting mergers and collisions that produce no light at all. And in the data streaming from these detectors, researchers have begun finding things that existing models struggle to explain. There is a background hum of gravitational waves permeating the cosmos. Unlike the sharp chirps produced by black hole mergers, this is a diffuse, continuous signal coming from all directions simultaneously. Pulsar timing arrays, which use spinning neutron stars as natural gravitational wave detectors by monitoring the extraordinary regularity of their pulses, have detected this background at frequencies far lower than ground-based detectors can access. Most of the proposed explanations for this background are conventional. The combined signal of supermassive black hole pairs orbiting each other at the centers of distant merging galaxies is the leading candidate. Cosmic strings, hypothetical defects in spacetime from the early universe, are another. Both could produce a background roughly matching what is observed. But some theoretical frameworks suggest more exotic origins. Gravitational waves propagate through space-time geometry itself. If extra dimensions exist and gravity propagates through them, gravitational waves generated in our universe would not be entirely confined to our three-dimensional slice. They would leak energy into the extra dimensions. And conversely, large-scale gravitational events in a neighboring brane universe, a massive merger or a structural collapse of enormous scale, would produce gravitational waves that could propagate through the extra dimensions and arrive at our detectors as a signal from a source we could never locate in any visible direction. We would detect a gravitational wave from nowhere, a ripple from an event that left no electromagnetic trace, pointing to no known merger in any catalog of observed objects. Unexplained events of this type have been noted, discussed, and set aside for lack of a conventional explanation. The field is young, the instruments are improving rapidly, and the catalog of unexplained signals is growing. Each one individually could be a measurement artifact or a known astrophysical source that was simply missed. Together, they represent an open question that more sensitive detectors will eventually be able to close. What makes gravitational waves particularly important as a probe of external interaction is that they carry information about the geometry of space-time at the source, not just the energy of an explosion or the mass of a merger. A gravitational wave from a domain wall collision between universes would carry within its waveform the signature of the domain wall geometry, a specific pattern that would be unlike any waveform produced by conventional astrophysical sources. Future detectors, operating across a wider range of frequencies and with greater sensitivity, will be capable of detecting and characterizing that kind of waveform. The question of whether anything fitting that description appears in the data is one that the next decade of gravitational wave astronomy will begin to answer. And the anomaly coming next involves something we have searched for exhaustively and failed to locate, no matter how hard we look, no matter how sensitive the instruments we use. At the moment of the Big Bang, the physics governing our universe should have produced equal quantities of matter and antimatter. For every particle of matter created by the energy of that initial moment, a corresponding antiparticle should have been produced alongside it, an electron and a positron, a proton and an antiproton, perfect symmetry, particle for particle all the way down. Matter and antimatter annihilate on contact. They convert entirely into energy. If the universe began with equal amounts of both, it should have annihilated itself completely in the first moments of existence, leaving behind nothing but radiation and empty space. Instead, we exist. The observable universe is made overwhelmingly of matter. Antimatter exists in nature, produced in cosmic ray interactions and radioactive decay. But there is essentially no primordial antimatter anywhere we have looked. The surveys are extensive and the conclusion is robust. Something in the very early universe treated matter and antimatter differently, producing a tiny asymmetry, a small excess of matter over antimatter, and that excess is everything we see. Every galaxy, every star, every atom on this planet, and every atom in your body is the residue of that imbalance. This is called the matter-antimatter asymmetry problem, technically the problem of baryogenesis, and it is one of the deepest unsolved problems in all of physics. The standard model of particle physics does include a mechanism for treating matter and antimatter differently, called charge parity violation. But the amount of asymmetry the standard model can generate is many orders of magnitude smaller than what must have actually occurred for us to be here. Something else created the imbalance. The physics required is not inside any confirmed model. Many extensions of standard physics have been proposed, new heavy particles decaying asymmetrically in the early universe, new types of neutrino physics seeding the imbalance at high energies, phase transitions in the early cosmos favoring one side over the other. None of these have been confirmed by experiment. One sobering implication appears repeatedly in theoretical discussions. The energy scales at which the required physics would have to operate are so high that no particle accelerator ever built or planned could reach them. The processes that selected matter over antimatter may have operated at conditions that existed only in the very first moments after the Big Bang, conditions tied to the initial state of the universe, conditions that may have been set by boundary conditions external to our universe rather than by anything arising within it. Something chose which way the universe would go. Something tipped the scales so decisively that billions of years later, you are here to read about it. Whatever made that choice has left no direct trace, only its outcome. And the next invisible force shaping our universe is already behaving in ways that suggest it too may be receiving instructions from somewhere we cannot directly look. The matter-antimatter problem is not merely a historical curiosity about an event that happened long ago. It is an active constraint on physics beyond the standard model. Every proposed mechanism for generating the asymmetry requires new particles, new interactions, or new symmetry-breaking processes that have not been detected. Finding any of them in next-generation experiments would be a breakthrough in its own right. The fact that none have been found yet means the physics that created us is still hiding from us, somewhere above the energies we can reach, possibly near the conditions that set the initial state of the cosmos itself. In 1998, two independent teams of astronomers were measuring the expansion of the universe and expecting to find it slowing down. Gravity pulls matter together, and the matter of the universe should have been applying the brakes to its own expansion. Both teams were trying to measure how quickly the brakes were working. What they found instead upended cosmology. The expansion was not slowing down. It was accelerating. Space was stretching apart at an increasing rate, growing faster with every passing era, as if some invisible force was pushing everything away from everything else with growing strength. They called this force dark energy, and its discovery earned the Nobel Prize in Physics in 2011. Dark energy is real. Multiple, completely independent lines of evidence confirm its existence and its effect. It constitutes roughly 68% of the total energy content of the observable universe, making it the dominant component of everything that exists, more than dark matter, more than all the ordinary matter in every star and galaxy combined. And we have no idea what it is at a fundamental level. The simplest model treats dark energy as the cosmological constant, a fixed energy density intrinsic to empty space itself. In this picture, the vacuum of space has an inherent energy, a property of empty space rather than of anything sitting in it. And that energy is perfectly uniform across all of space and constant across all of time. New data is creating serious problems for this simple model. Results released in 2024 from a major galaxy survey, after mapping more than 6 million galaxies across a large fraction of the observable cosmos, showed hints that dark energy may be evolving over time. The data suggests the strength of the dark energy effect may be changing as the universe ages, becoming stronger or weaker in ways that a true cosmological constant absolutely cannot do. A constant, by definition, does not vary. Dynamic dark energy, called quintessence in the theoretical literature, would be a field permeating space that can change its value over time. A field, unlike a constant, has a history. Its current value is the result of a process, not a fixed property. And a process has causes. If dark energy is a field, then something set its initial value. Something determined the conditions under which it began and the direction in which it has been evolving. Those initial conditions were set at the beginning of the universe, at or near the Big Bang. And the most troubling theoretical analyses suggest that the specific value of dark energy we observe today, the peculiarly small value that allows matter to exist rather than being immediately ripped apart or pulled back together, cannot be explained by any process internal to our universe. The value looks tuned. Something external may have tuned it. And if that something is still affecting dark energy's evolution, its influence has been shaping the entire history of cosmic expansion. The evolving dark energy measurement also carries a specific implication for how external influence would manifest. If a neighboring universe or brane is slowly approaching our own, the energy in the boundary between them would change over cosmic time. That change would appear in our universe as a dark energy value that is not constant. The hints of evolution in dark energy may be, in the most literal sense, evidence that our universe's boundary conditions are changing. Something outside is moving, and its motion is leaving a signature in the expansion rate of everything we can see. Our observable universe has a hard edge. Light travels at a fixed speed. The universe has a finite age, and that combination means there is a maximum distance from which any light could have possibly reached us since the Big Bang. Everything beyond that distance is, in principle, forever invisible to us. The light from those regions can never arrive because the expansion of space is carrying them away faster than light can cross the gap. That sphere of reachable observation surrounding us is called the particle horizon, and it represents the absolute limit of any direct measurement we could ever make. Everything we know, every model we have built, every theory we have tested is based entirely on what happens to exist inside this particular bubble of causality. For most of scientific history, this seemed like an abstract limitation with little practical consequence. The physics inside our bubble was assumed to be representative of the physics everywhere else. The universe should look the same in every direction and from any location at large scales. Our bubble's contents should be a fair sample of the whole. But the evidence has been accumulating that this assumption may be wrong. The axis of evil points in a specific direction, breaking the expected symmetry. The large-scale asymmetry in the oldest radiation background shows the two hemispheres of the sky are different in ways they should not be. Dark flow points toward a specific region beyond our horizon. The Great Attractor exerts more pull than its visible mass justifies. Each of these anomalies, taken individually, could be explained by some unusual fluctuation inside our bubble. But they share a common character. They all suggest a preferred direction, a preferred region, a systematic bias that points toward something outside what we can directly see. What if our particular bubble of observable space has unusual properties arising from where it sits in the larger structure rather than from any random internal fluctuation? What if we are located near the edge of a larger feature, adjacent to a structure in the full universe, or near the influence radius of a neighboring brain, and the anomalies we observe are the gravitational and energetic shadow of that adjacency? A fish in the deep ocean cannot see the coast, but it can be carried by currents produced by the shape of the seafloor thousands of meters below. The currents are real. The fish can measure them. The shape of the seafloor that produces them is forever invisible. We may be the fish, measuring currents we can detect but cannot trace to their source, because the source lies beyond the boundary of the only ocean we can see. We cannot look past our horizon directly. Every attempt to detect what lies beyond must be indirect, and physicists have spent the last 2 decades developing methods to do exactly that. Those methods are now real, funded, and running. What they have found so far is stranger than most expected, and the signs that something external is pressing on our universe from beyond that horizon are written into the data we already have. The anomalies are inside the boundary. The influence, if real, arrived from outside, and physicists have spent the last 2 decades developing the tools to tell the difference between an internally generated anomaly and one that carries the fingerprints of an external cause. Those tools are now running, and the question of whether something beyond our universe is interacting with us has crossed from untestable speculation into active empirical investigation. Given that another universe, by definition, cannot be observed directly, physicists have had to become deeply creative about how they might detect one indirectly. The methods they have developed are precise, grounded in real theoretical predictions, and increasingly capable with every improvement in instrumentation. The first approach is the collision scar search. A collision between our bubble universe and a neighboring one would leave a circular temperature anomaly in the cosmic microwave background, with a specific profile calculable from the physics of the collision. Researchers have built algorithms to search the background radiation data for exactly this kind of feature, looking for circular regions with the predicted temperature gradient and edge sharpness. Multiple searches have been run on data from 2 major satellite missions. Results have been inconclusive in the sense that they have found candidates without being able to rule in or rule out the collision interpretation definitively. Next-generation missions with higher resolution may close that gap. The second approach uses gravitational wave astronomy at the lowest accessible frequencies. A space-based gravitational wave observatory, currently in development by the European Space Agency, will be sensitive to frequencies far below what ground-based detectors can reach. Theoretical models predict that domain wall dynamics between adjacent universe bubbles or the large-scale structural events of a neighboring brane universe would produce gravitational wave signals in exactly this low-frequency range. The observatory will be capable of detecting them if they are present. The third approach examines the statistical properties of large-scale structure. If something external is exerting gravitational influence on our universe, the distribution of matter across hundreds of millions of galaxies should show a systematic bias, a subtle directional preference that would not appear in a perfectly self-contained universe. 2 major galaxy surveys currently operating, covering enormous fractions of the sky to unprecedented depth, will accumulate enough data to detect or rule out this kind of bias over the next decade. Each of these approaches is genuinely falsifiable. Each makes specific predictions about what data should look like if external interaction is real. Each uses instruments that exist or will exist within this decade. The question of whether something beyond our universe is interacting with us is, for the first time in history, a question that real experiments can begin to answer. The phrase extra-universe detection would have been dismissed as science fiction 3 decades ago. Today, it appears in serious grant applications and peer-reviewed proposals at the world's most respected research institutions. The transition from untestable speculation to empirical science is the most important shift that can happen in physics, and it is happening right now in this field. But the evidence is not only in the sky. The equations themselves have been pointing at something outside for years. There is a fourth approach worth noting that works across all frequency ranges. Statistical patterns in the polarization of the microwave background carry information about the geometry of the universe at the very largest scales. If our universe has a preferred axis introduced by external influence, that axis would appear in the polarization statistics in a way distinct from anything produced by internal processes. Next-generation missions will map that polarization with far greater precision than any existing instrument. The data they return will either confirm or rule out the directional signatures that external influence would produce. The answers are coming. The cosmic microwave background is the universe's oldest photograph, taken at the moment 380,000 years after the Big Bang, when matter and light first separated, and radiation could finally travel freely through space. Everything that happened before that moment, and every large-scale gravitational influence that has shaped our universe since, has left some trace on that light. The difficulty is knowing which traces are internally generated and which might have been pressed into the photograph from outside. Internal imprints are well understood and match observations with extraordinary precision at most scales. The pattern of quantum fluctuations amplified by inflation produces a specific statistical signature in the temperature variations, and that signature appears exactly as predicted across the vast majority of the sky. The acoustic oscillations in the early plasma, primordial sound waves in the hot gas of the young cosmos, leave a specific pattern in the temperature correlations that astronomers now use as a precise measuring tool across billions of light years. But the anomalies we have described throughout this journey do not belong to the internal catalog. They are marks in the photograph that the known internal processes did not put there. In universe collision physics, a collision would leave a disc-shaped imprint with specific properties, a circular boundary where the temperature drops or rises sharply, a characteristic temperature profile inside the disk predicted by the geometry of the collision, and a size on the sky determined by how far away the collision occurred and how strong it was. The cold spot has a circular shape and an anomalous temperature profile. The match to collision predictions is partial, which means either the models need refinement or the cold spot has a different origin. In brain cosmology, a neighboring brain exerting gravitational influence on our early universe would distort the density fluctuations in the primordial plasma in a directional way. The plasma on the side of our universe facing the neighboring brain would be squeezed differently than the plasma on the far side. That asymmetry would appear in the temperature map as a systematic difference between two hemispheres of the sky. The large-scale asymmetry found in multiple independent analyses of the microwave background is exactly this kind of hemispheric difference. Neither match is conclusive. Cosmology requires extraordinary caution in interpreting anomalies in a single, unique data set. But the theoretical frameworks that produce these predictions were developed before the searches were run, and the anomalies found match what was predicted closely enough to keep serious researchers actively pursuing the question. What the mathematics underneath these observations is also saying is in some ways even more unsettling than the observations themselves. When physicists talk about reading the history of the universe in the microwave background, they mean it literally. Every feature in that ancient light is a record of something that happened in the first moments of cosmic time. The anomalies are records of something our standard history does not include, and the mathematics governing what they could mean has been demanding for decades that the history our universe carries inside itself may have been written partly from outside. That demand comes from the sky maps and from the equations alike. The mathematics has been pointing at precisely this for decades. The next chapter shows how clearly and how persistently. Sometimes the most alarming implications in physics come from equations rather than from what telescopes find. When the mathematics of a theory works perfectly, but only by importing a value from outside the system the theory describes, that is a signal. Something is missing. The theory is reaching for something it cannot supply internally. Modern cosmology has several places where the mathematics does exactly this. The most famous is called the cosmological constant problem, quantum field theory, the framework describing particles and forces with extraordinary precision in laboratory experiments, predicts that empty space should be filled with an enormous amount of energy from quantum fluctuations. The predicted value is roughly 1 followed by 120 zeros times larger than the dark energy we actually measure. This discrepancy is the largest in the entire history of physics. Some mechanism must be canceling virtually all of that predicted energy and leaving only an unimaginably tiny residue. No internal mechanism within standard physics has been found that can do this. The most mathematically consistent framework for thinking about this problem involves a landscape of possible vacuum states, a vast collection of possible universes, each with different values of vacuum energy, and some selection process determining which value our universe inhabits. The selection process is external to the physics of any individual universe. The mathematics requires something outside to have chosen the value we measure. The initial conditions of the Big Bang present a similar problem. Physics can describe the evolution of the universe forward from a tiny fraction of a second after the beginning, but the state the universe was in at that moment was extraordinarily special in ways that cannot be explained internally. The universe was smooth and flat, to a precision that should have been overwhelmingly unlikely if those conditions were chosen at random from all possible starting states. Inflation resolves some of this by wiping out irregular geometries, but inflation itself requires specific initial conditions to begin. The regress continues backward until you reach a moment where the mathematics simply says, the values were set this way. Something set them. That something is outside the system the equations describe. This is an argument from mathematical structure, not from anomalies in data. But the force of it is significant. The equations that best describe our universe consistently reach past the edges of our universe for explanatory input. They require external boundary conditions. They demand an outside. And they have been doing this since long before anyone started finding anomalies in galaxy surveys and satellite maps. The frameworks proposing to supply that outside have their own internal structure, revealed most fully in a theory that rewrites the foundations of what matter and space even are. The fine-tuning problem itself is a well-established observation, known since the early 20th century. What has changed is that the mathematical frameworks developed to address fine-tuning consistently require external input to work. The landscape of possible vacuum energies, the multiverse generated by eternal inflation, the brain-world geometries of string theory, all of these are frameworks that place our universe inside a larger structure and explain the values of our constants by reference to selection within that structure. The mathematics does not suggest an outside as a speculative possibility. It requires it as a logical necessity. String theory is the most mathematically developed candidate for a complete description of nature, a framework attempting to unify gravity with the other fundamental forces in a single, coherent picture. It is not confirmed by experiment, and it has serious critics within the physics community. But it is the most internally consistent theoretical framework physicists have constructed for this purpose, and it has produced genuine mathematical insights that have influenced fields far beyond its original scope. String theory requires extra dimensions of space. In the framework, the elementary constituents of nature are tiny, vibrating strings of energy rather than the point particles of standard physics, and the different ways a string can vibrate correspond to different particles. For the mathematics to be consistent, these strings must vibrate in a space with 10 dimensions, not 3. Our experience of 3 spatial dimensions means that the other 7 must be hidden, curled up into shapes too small to detect at any energy accessible to existing technology. Those extra dimensions are not empty. They have specific geometric shapes, and crucially, the shape of the extra dimensions determines the physical laws experienced by matter living in the three-dimensional space built on top of them. Different geometric configurations produce different particle masses, different force strengths, different values of the cosmological constant. The landscape of possible geometric configurations produces a landscape of possible universes, each with its own distinct physics. Our universe is one point in that landscape. The physical constants we measure, the mass of the electron, the strength of the strong nuclear force, the specific value of dark energy, are not fundamental. They are determined by the geometry of dimensions we cannot see. They are, in a sense, accidents of which geometric configuration our region of space-time ended up in. Now, consider what happens when two brains share their extra-dimensional geometry. If our universe and a neighboring brain exist in the same bulk space with the same extra-dimensional structure, they are structurally coupled through that geometry. The extra dimensions are not separate for each brain. They are shared. Changes in the shared geometry, driven by the dynamics of either brain, would affect the physical laws experienced in both. A neighboring brain approaching our own in the extra dimension would alter the geometry of the shared extra dimensions. That alteration would manifest in our universe as a changing physical constant. Dark energy evolving over time, the strength of gravity shifting, the mass of particles drifting in ways our experiments would eventually detect. There is a version of this picture called ekpyrotic cosmology, in which our Big Bang itself was caused by such a collision between two brains. In this model, the universe began with the collision of two flat parallel membranes that had been drifting toward each other through the extra dimension rather than from a singular compressed point. The collision released enormous energy and set our universe expanding. The other brain exists still, on the other side of the boundary, carrying its own version of physics into its own future. The mathematics is serious. The implications for what we are and where we came from are extraordinary, and what this framework implies about what interaction between universes could actually mean is worth examining carefully and precisely. Our universe is one point in that landscape. The constants we measure were set by the geometry of dimensions we cannot see or access, and in some versions of the mathematics, that geometry can change over time as the brain evolves, meaning the constants themselves might drift slowly across cosmic history. When scientists use the phrase external interaction to describe something beyond our universe affecting us, the word interaction carries precise technical meaning. It does not mean communication. It does not mean intelligence or intention. It means a physical influence, one region of space-time exerting a force or transferring energy to another through a defined physical mechanism. That distinction matters enormously. The proposed mechanisms fall into several well-defined categories, each with specific observational predictions. The first and most developed mechanism is gravitational. Gravity propagates through all dimensions of space-time, including any extra dimensions connecting our universe to adjacent regions. A mass concentration in a neighboring brain, or bubble universe, would exert gravitational attraction on matter in ours. The effect would be directional, pointing toward wherever that mass concentration is located relative to our position in the higher dimensional geometry. At local scales, the effect would be subtle, but summed across the observable universe, it could be enormous, manifesting as a coherent bulk flow of galaxy clusters toward the region of influence. The second mechanism involves energetic boundary effects. In bubble universe cosmology, the domain wall separating adjacent universes carries energy. If that wall is dynamic, If two adjacent bubbles are slowly drifting toward or away from each other, the energy stored in the boundary changes over time. Energy stored in a boundary between our universe and a neighboring one could couple to the vacuum energy of our cosmos, appearing to us as a changing dark energy. The evolution of dark energy that recent galaxy surveys seem to be detecting could be a boundary condition imposed from outside, updating as the boundary itself evolves. The third mechanism is the most speculative. Some interpretations of quantum mechanics suggest that quantum entanglement is not merely a correlation between particles within a single universe, but a feature of the full quantum wave function that may span multiple branches or bubbles. If our universe and neighboring ones share a quantum mechanical origin, there may be correlations between them that appear in our data as anomalous statistical patterns, alignments, or regularities that have no internal causal explanation. Each of these mechanisms makes specific predictions. The gravitational mechanism predicts directional anomalies in large-scale structure. The boundary energy mechanism predicts specific patterns in how dark energy evolves. The quantum mechanism predicts statistical anomalies in the distributions of certain observables. Every anomaly we have discussed matches at least one of these predictions, and several match more than one. The agreement is imperfect, as it always is between theoretical predictions and real, noisy data. But it is consistent enough that serious physicists are building careers around the hypothesis that external interaction is real, testable, and perhaps already detected in the data we already have. There is a reason the word interaction is carefully chosen here rather than contact or communication. Interaction in the physical sense is impersonal and automatic. Gravity does not choose to pull. It pulls because mass curves space-time, and curved space-time determines how objects move. If a neighboring universe is pulling on ours gravitationally, it is doing so for the same reason that our star pulls on our planet. There is no will involved. There is no signal being sent. There is only geometry operating the way geometry always operates. This means the detection of external interaction, if it comes, will not look like receiving a message. It will look like noticing that gravity is coming from a direction where there is nothing visible to produce it. It will look like measuring a constant of nature and finding it has changed in a way that cannot be explained by anything inside our universe. Before completing this journey through the physical evidence, it is worth acknowledging a parallel framework that some serious thinkers have proposed as an alternative explanation for the same anomalies. It is philosophically distinct from the physics discussed so far, but converges on a remarkably similar conclusion. Something outside our universe may be determining conditions inside it. The simulation hypothesis begins with a straightforward observation about the trajectory of computing technology. Processing power has grown by orders of magnitude over the last century, and there is no obvious physical reason why it must stop. A civilization sufficiently advanced in its technological development might eventually be capable of running a computational simulation of a universe detailed enough that inhabitants inside it could not, through any internal measurement, distinguish their simulated existence from a base physical reality. The philosopher Nick Bostrom formalized this into a precise argument in 2003. Either nearly all civilizations destroy themselves before reaching the computational capability for universe simulation, or nearly all civilizations capable of such simulation choose never to run it, or we are almost certainly living inside such a simulation right now. At least one of those three things must be true, and if the first two are false, the third follows from basic probability. The hypothesis is not falsifiable in its strongest form, which is one reason physicists handle it cautiously, but it is relevant here because it offers a coherent alternative interpretation of every anomaly in this discussion. The Hubble tension could be a precision error in the underlying computational model. The cold spot could be a resolution artifact at the edge of a simulated region. The axis of evil could be a boundary condition imposed by the geometry of the simulation's computational grid. Dark energy's apparently evolving value could be a parameter being adjusted by whoever is running the computation. These interpretations are structurally identical to the multiverse explanations at the level of their logical form. In both cases, the anomalies are explained by reference to something external that set or is adjusting the conditions inside our universe. The physical multiverse says that external thing is another region of space-time with its own physics. The simulation hypothesis says it is a computational substrate with its own physics. The difference between them is real and worth examining, though the scientific challenge they both present is the same. How would you tell? What makes this worth considering seriously is not that it is likely to be true. It is that its logical structure is shared with the most mainstream cosmological frameworks now being tested by real experiments. The question of external influence is the same question regardless of which framework asks it. And the next place physicists are trying to answer it is in laboratories here on Earth. The simulation and multiverse frameworks actually make overlapping predictions in several important domains. Both predict that certain constants of nature could be different in neighboring regions of the larger structure. Both predict that the boundary between our region and neighboring regions might have left an imprint on the oldest observations. Both predict that there should be some way to probe the structure of the boundary if sufficiently sensitive instruments could be built. Where they differ is in what would be found if the search succeeded. In the multiverse framework, a confirmed detection would reveal another region of physical space-time with its own matter and its own history. In the simulation framework, a confirmed detection would reveal the computational architecture supporting our reality. The difference is philosophically enormous, but experimentally subtle, at least with instruments available in any near future. The most direct experimental test of whether extra dimensions exist is also the simplest conceptually. Measure gravity at short distances and look for deviations from the expected behavior. Gravitational attraction between two masses follows an inverse square relationship. Double the distance between them, and the attractive force drops to 1/4. This law has been tested over an enormous range of distances, from planetary orbits down to scales measurable in laboratories. Everywhere it has been tested, it holds. But at very short distances, smaller than the scale at which any extra dimensions might be curled up, the law should break. If extra dimensions exist and gravity propagates through them, then, at distances shorter than the extra dimension size, gravity would spread into those dimensions and become stronger than the inverse square law predicts. Measure gravity precisely enough at short enough distances, and you would find it pulling harder than it should. The most precise short-distance gravity measurements in the world have been conducted by a research group at the University of Washington using extraordinarily sensitive torsion balance instruments. These devices can detect gravitational forces between metal disks separated by gaps smaller than the width of a human hair. Their measurements have found no deviation from the inverse square law down to scales of roughly 56 micrometers. This constrains, but does not eliminate the possibility of extra dimensions. It means any extra dimensions large enough to affect gravity at the scales tested must not exist. Any extra dimensions that do exist must either be smaller than the tested scales or must have a geometry that suppresses the gravitational deviation below the sensitivity of current instruments. At the Large Hadron Collider, particle physicists have searched for signs of extra dimensions through a different mechanism. If gravitons, the hypothetical carriers of gravitational force, can propagate into extra dimensions, then collisions at very high energies should sometimes produce events where energy appears to disappear, carried away by gravitons escaping into dimensions we cannot detect. These missing energy signatures have been searched for in collision data accumulated over many years of operation. No definitive signal has been found. A planned future circular collider with collision energies roughly 5 times higher than anything currently achievable would push the search into energy ranges that current instruments cannot access. Space-based gravitational wave observatories will probe frequency ranges where signals from extra-dimensional dynamics are predicted to appear. Planned experiments in quantum gravity phenomenology will test whether the mathematical structure of extra-dimensional theories leaves any imprint in precision atomic measurements. Each search has so far returned silence at the level of its sensitivity. Each next search pushes further into unexplored territory. The absence of a signal is a constraint, narrowing the space of possibilities, not a disproof, closing the question. The question remains open, and what it would mean for our civilization if one of these searches finally returned something other than silence is worth examining with complete seriousness. Each search has so far returned silence at the level of its sensitivity. Each next search pushes further into unexplored territory. The absence of a signal is a constraint, narrowing the space of possibilities. The extra dimensions, if they exist, must be smaller than the scales already tested, or their geometry must suppress the detectable deviation below current thresholds. The next generation of colliders and gravitational observatories will push into regimes qualitatively beyond what exists today, accessing energies and frequencies where the predicted signals would be unmistakable if they are present. The question remains open, and what it would mean for civilization if one of these searches finally returned something is worth examining with complete seriousness. 2 decades ago, the word multiverse barely appeared at major cosmology conferences except in dismissive asides. Physicists who brought it up in research presentations risked having their work treated as philosophy rather than science. The idea that something beyond our universe could be interacting with us was considered untestable, and untestable ideas have no place in empirical science. That has changed substantially, and the change is worth understanding in detail because it tells you something important about where the field now stands. The shift began with the anomalies. One anomaly in a cosmological dataset is routine. 2 anomalies are a coincidence. 5 anomalies that all point in the same conceptual direction, that all suggest something the standard model did not predict and cannot easily explain, begin to feel like a pattern. The cold spot persisted across improving data sets. The Hubble tension grew more precise and more stubborn with every new measurement campaign. The axis of evil survived the transition from one satellite mission to another with better instruments. The large-scale asymmetry refused to disappear as foreground removal improved. Each individual anomaly might be explicable by adjusting some internal parameter. Explaining all of them simultaneously without invoking something new became increasingly difficult. The second driver was theoretical maturation. String theory, inflation cosmology, and brain world physics advanced from qualitative frameworks to mathematically precise theories, making specific, quantitative, falsifiable predictions. The shift from "this might leave some kind of imprint" to "a collision at this distance and strength would produce a temperature anomaly of exactly this profile in this location" is the shift from speculation to science. Once a theory makes a prediction specific enough to test, it belongs in physics. The third driver was instrumentation. Galaxy surveys mapping hundreds of millions of objects. Satellite missions producing microwave background maps of extraordinary resolution. Gravitational wave detectors capable of measuring displacements smaller than a proton. Pulsar timing arrays accumulating decades of precisely timed pulses. These instruments produce data sensitive enough to detect the signals that theoretical models predict, if those signals are present. Leading research groups at institutions including major European universities, American research universities, government space agencies, and national laboratories are actively conducting research explicitly aimed at testing these ideas. Papers on multiverse collisions, brain-world gravity, and large-scale structural anomalies appear regularly in the highest-ranked peer-reviewed journals. Funding agencies in multiple countries support this research with substantial budgets. The frontier of physics is the edge of what is currently testable. These questions sit at that edge. And in the history of science, the questions that sit at the frontier are almost always the ones whose answers arrive next. The shift in how seriously this work is taken also reflects a broader maturation in how physicists think about testability. A generation ago, the dominant view was that a scientific theory must make predictions testable with current or near-future technology. Anything else was philosophy. That standard was applied rigorously to multiverse theories and used to dismiss them. The standards remain the same. The technology has transformed. The gap between what a theory predicts and what an instrument can detect has narrowed substantially. Theories that predicted signatures in the microwave background were untestable in the 1980s and testable with precision by 2010. Theories predicting gravitational wave signals from cosmic-scale events were untestable before 2015 and have been in the active detection program of multiple observatories since. The theories asking whether something beyond our universe is interacting with us have now generated specific quantitative predictions. Those predictions point at instruments that either exist or are funded and under construction. Imagine the announcement: a press conference unlike any other in the history of science. The world's leading cosmologists standing together to state with statistical confidence that the universe they have spent their careers studying is embedded in something larger, that evidence of external influence has been found in the data, and that the standard model of a self-contained universe must be replaced with something far more complex. The implications would cascade through every domain of human thought and organization. For science, the immediate consequence would be the collapse of the cosmological principle in its current form. The assumption that our universe is causally self-contained, that every physical constant and initial condition was determined entirely by internal processes, would be overturned. Cosmology would require a new foundation, one that treats our universe as a component of a larger system rather than as the total system. Every simulation of cosmic structure, every model of the universe's past and future, every theory built on the assumption of self-containment would need to be reconsidered from the beginning. For fundamental physics, confirmed extra dimensions, or confirmed inter-universal gravitational coupling would validate aspects of string theory that no current experiment has managed to test. It would open the question of what the larger structure looks like, how many universes exist, whether the laws of physics are fixed or vary from bubble to bubble, and whether the laws of our bubble can change over time as boundary conditions evolve. Physics would enter a period of reconstruction comparable to the aftermath of quantum mechanics, when a century of classical physics had to be rebuilt on a new foundation. For our understanding of the constants of nature, confirmation would mean that the specific values of physical law we experience are not the only possible values, and that our values were selected by some process, whether inflationary dynamics, boundary conditions from a collision, or gravitational coupling to a neighboring brain. The values that make chemistry possible, that allow stars to burn at the right rate, that permit atoms to form and life to exist, would be understood as outcomes of a selection, not as inevitable features of the universe. For philosophy and for every tradition of human thought concerned with the nature of reality, the implications would extend further than any single discipline. Every civilization that has ever existed has asked whether the world it inhabits is all that exists. Every tradition has proposed its own answer. Confirmation of external influence on our universe would be the first empirical answer to that question, and it would be an answer that says the universe we live in, as vast and ancient and incomprehensible as it is a small part of something larger still. The announcement has not come. The evidence is suggestive, not conclusive. The anomalies remain anomalies, but the question has moved from untestable to testable, and from philosophy to physics. There is something worth sitting with in the gap between where we are and where a confirmation would take us. We live at a moment when the question is genuinely open. The data is ambiguous enough that both answers remain possible. The instruments are good enough to have found hints, but not yet good enough to have found proof. We are, in the language of physics, still in the prior phase, still in the state of having enough evidence to take the question seriously, but not enough to close it. That ambiguity is uncomfortable for a civilization accustomed to looking to science for certainty. But it is the honest scientific situation, and it is worth describing honestly. The light is still coming. Right now, at this moment, the cosmic microwave background is passing through your body at the speed of light, washing through every atom, carrying within it the oldest information in the observable universe, 2.7 degrees above absolute zero, arriving from every direction with equal intensity, except where it is not quite equal, except where the anomalies sit embedded in its ancient pattern. Somewhere in that light is the cold spot. Somewhere in the orientation of its largest features is the axis that should not align with anything in our solar system. Somewhere in the expansion rate of the galaxies around us is a number that does not match what the ancient light predicts it should be. Here is what is confirmed. The Hubble tension is real, measured by independent teams using independent instruments, and it has not gone away with better data. The cold spot is real, present in maps produced by multiple satellite missions, unexplained by any conventional mechanism that fully closes the case. The large-scale asymmetry in the background radiation is real, confirmed by independent analyses persistent across instrument generations. Dark energy shows hints of evolving over time in the most comprehensive galaxy survey ever completed. These are measurements, they are data, they belong to the universe and not to any particular theory about it. Here is what is a theory. The explanations involving neighboring universes, extra dimensions, brain collisions, and external gravitational coupling are scientific hypotheses. They make specific predictions. Those predictions are being tested by real instruments. They have not been confirmed, and they have not been definitively ruled out. They sit in the state that all good scientific hypotheses occupy before the decisive experiment, possible, motivated by evidence, and waiting for a test precise enough to decide. Here is what remains unknown: whether the anomalies have internal explanations that have simply not been found yet, whether the theoretical frameworks pointing outside our universe are the right frameworks or elaborate mathematical structures that happen to fit the available noise, whether the next generation of surveys and detectors will find a signal or find silence, whether the question of external influence will be answered in 10 years or 100 or never. And here is what matters regardless of the answer. We built instruments sensitive enough to detect a ripple in space-time smaller than a proton. We mapped the oldest light in the universe with enough precision to find features a fraction of a degree across. We measured the expansion of space across billions of light years with enough accuracy to notice a discrepancy in the seventh significant figure. We did this by asking questions that began with the simplest possible form: what is out there, and how do we know? The signal is arriving. We are learning to read it. And somewhere in the oldest light in existence, in the motion of galaxy clusters, no model fully predicts. In the equations that keep reaching past their own edges for an answer, something is telling us that what we can see is not all there is. We have not yet learned what the rest looks like, but for the first time in history, we have built tools capable of finding out. The oldest light is still coming. The signal is still arriving. And somewhere in it, pressed into the ancient pattern by forces that may have acted from beyond every boundary we know, is an answer we have not yet learned to read clearly enough to trust. But we are closer than we have ever been, and the instruments being built right now are the most powerful we have ever aimed at the question.